There's something about the way stars look on a clear night, still, unchanging, as if they've always been there and always will be. We glance up between the branches of trees or over the roof of a building, and they're just there, constant, patient, waiting for nothing in particular. And maybe that's what makes them feel so different from almost everything else we know. Because when we think about fire, when we think about burning, we think about things that consume themselves. A candle melts down over the course of an evening. A campfire crackles and fades by morning. Even the sun setting feels like the end of something, even though we know it will rise again. But stars do something we can't quite reconcile with what we understand about burning. They've been shining for billions of years. Not days, not decades, billions of years. The same stars that hang above us tonight were already ancient when the first humans looked up and wondered what they were, and they'll still be there, most of them, long after we're on. So the question isn't really about how stars burn. It's about how they manage to burn so slowly, how they hold all that energy inside themselves without simply exploding in an instant, how they ration something as violent as nuclear fusion across timescales we can barely imagine. We're going to stay here for a while tonight and think about that together. Not because we need to solve it, but because it's one of those questions that feels bigger the longer you sit with it. And there's no rush. There never is with stars. You can close your eyes if you'd like. You can let the screen fade into the background. We're not going anywhere quickly, and neither are the stars. What we're really asking is this: why don't stars use up everything they have all at once? What keeps them from burning through their fuel in a flash of light and then going dark? It's not something we usually think about. Stars just seem permanent, like mountains or oceans, things that were here before us and will remain. But nothing burns forever without running out, and yet stars come closer to forever than almost anything else we know. The answer, when we find it, won't feel like a revelation. It'll feel quieter than that. More like noticing something that was always true but easy to overlook. That's how most things in space seem to work. Not sudden, not dramatic, just unfolding slowly across distances and durations that make our entire lives feel like a single breath. So we'll take our time. We'll start with what we know about fire, the kind we can see and touch and understand, then we'll move outward gently into what stars are actually doing when they shine. Not burning exactly, something else, something that requires a different kind of patience. And maybe, by the end of this, we'll understand not just why stars last so long, but why the universe seems built for slowness in the first place. Why balance, not explosion, is the default. Why most things that endure do so quietly. For now, just know this: the stars above you have been doing this for longer than anything else you can point to, and they'll keep doing it steady and sure. Long after this night ends, we're here together, and we have all the time we need. When we think about fire, we think about something hungry. A match strikes and catches, and immediately it's consuming itself. The wood darkens, the flame climbs, and within seconds it's already burning through the thing that gave it life. There's no pause, no hesitation, just this immediate, unstoppable transformation from solid to heat and light and ash. We grow up around fire in one form or another: birthday candles that melt while we sing, firewood that crackles and pops and turns to embers by the time we're ready for bed. Even the gas flame on a stove, it appears instantly when we turn the dial, and it disappears just as quickly when we turn it off. Everything about fire in our experience is temporary. And that makes sense to us. We understand it. Fire needs fuel, and fuel runs out. The more intense the fire, the faster it consumes what it has. A small candle might last for hours. A bonfire might last through the evening. But nothing burns indefinitely, nothing we've ever seen anyway. So when we look up at stars and we're told they're burning, that they have been burning for billions of years, something doesn't quite add up. Because if stars are fires, they should behave like fires. They should consume themselves quickly. They should flare bright and hot and then fade, leaving nothing behind but darkness and cold, and yet they don't. The sun has been shining for 4.5 billion years. 4.5 billion. Every morning it rises, and every evening it sets, and it never seems to weaken, never seems to dim. It just continues steady and reliable, as if it has an endless supply of whatever keeps it going. But we know nothing is endless. We know that fuel, no matter how much of it there is, eventually runs out. There's this tension, this quiet contradiction between what we expect fire to do and what stars actually do. And maybe that's the first thing we need to sit with, the idea that stars aren't really fires at all, even though we use that word. They're something else, something that looks like burning from a distance but operates by completely different rules. When you light a candle, the wax reacts with oxygen in the air. It's a chemical reaction, fast, straightforward, limited by how much wax and oxygen are available. The flame consumes the candle from the outside in, and when there's nothing left to react with, the flame goes out. That's fire as we know it. And it's always temporary because chemistry itself is temporary. Reactions happen quickly, they release their energy in bursts, they end. But stars aren't doing chemistry. They're doing something deeper. Something that happens not at the surface, not in the presence of air, but at the core, in a place where the rules change, where pressure and heat become so extreme that atoms themselves start to change. And that process, whatever it is, doesn't happen all at once. It happens slowly, impossibly slowly, across timescales that make our familiar fires look like flickering sparks. So before we can understand why stars last so long, we have to let go of the idea that they're burning the way campfires burn. They're not. They're doing something quieter, something more patient. And that difference, that shift from chemistry to something else, is where the answer begins. We'll get there, slowly. The way stars do everything. There's a word we use when we talk about stars, and it's easy to miss how important it is. We say stars shine, not burn, not ignite, they shine. And maybe that's closer to the truth than we realise, because shining and burning aren't quite the same thing, even though they both produce light, even though they both produce heat. When something burns, really burns the way we understand it, it's breaking apart. Molecules are coming undone, bonds are snapping. Energy that was stored in the structure of the fuel is being released quickly into the air around it. It's a kind of falling apart, a controlled collapse, and it happens at the surface, in the presence of oxygen, in the world we know. But stars aren't breaking things apart. Not in that way. They're doing the opposite. They're pushing things together, deep inside a star where the pressure is so intense we can barely imagine it. Hydrogen atoms are being forced closer and closer until they can't stay separate anymore. Until they fuse, until they become something new, helium. And in that transformation, in that moment of joining rather than breaking, energy is released. Not because something fell apart, but because something came together. That's fusion. And it's nothing like the fire we know. It doesn't need oxygen, it doesn't happen quickly, it doesn't consume from the outside in. It happens at the core, in darkness, in a place so hot and so pressurized that the normal rules, the rules that govern candles and campfires, don't apply anymore. And here's the thing about fusion, it's slow. Not because stars are careful, not because they're rationing their fuel on purpose, but because the conditions that allow fusion to happen are so extreme, so specific, that it can only occur in the very centre of the star, only in that tiny, impossibly dense core where the pressure is greatest. The rest of the star, the vast majority of it, is just waiting, holding that core in place, pressing inward with the weight of its own gravity, creating the conditions but not participating in the reaction itself. So when we see a star shining, we're not seeing the whole star burn. We're seeing the light that escapes from a reaction happening in a space smaller than we'd expect. A reaction that happens slowly, steadily, one fusion at a time. Imagine if a campfire could only burn in a single spot at the centre of the log, and the rest of the wood just sat there, pressing inward, waiting its turn. That's closer to what a star does. The hydrogen in the outer layers isn't fusing. It's not doing anything yet. It's just there, patient, held in place by gravity, and it might wait billions of years before it ever gets its turn, if it gets a turn at all. This is why stars last so long. Not because they have an infinite amount of fuel, they don't, but because only a tiny fraction of that fuel is being used at any given moment. The reaction is bottlenecked by the conditions required to make it happen, and those conditions only exist in the core. So while fire consumes everything it touches, fusion only touches what's already at the centre. Everything else waits. And waiting, as it turns out, is what allows stars to shine for billions of years. It's not dramatic, it's not explosive, it's just this quiet, patient process. Atoms joining, energy releasing, light travelling outward through layers and layers of waiting hydrogen, till finally, eventually, it reaches the surface and escapes into space. By the time we see it, that light has already been travelling for thousands of years just to get out of the star itself. Shining isn't fast, it just looks that way from here. If you've ever held something heavy for a long time, you know how constant pressure feels. At first it's nothing, manageable, you barely notice it. But as the minutes pass, that weight becomes the only thing you can think about. It's always there, always pulling, never letting up, not even for a moment. Gravity is like that, except it never gets tired, and it never stops. Every part of a star is pulling on every other part. The hydrogen at the surface is pulling inward, the helium in the core is pulling inward. Every atom, every particle is trying to fall toward the centre, trying to collapse in on itself. And if that were the only force at work, stars wouldn't exist at all. They'd just be points of infinite density, collapsed, crushed under their own weight before they ever had a chance to shine. But they don't collapse, they hold their shape. They stay round and luminous and stable for billions of years. So something must be pushing back, and that something is the energy being released in the core, the heat and pressure from all those hydrogen atoms fusing together. Every time fusion happens, it releases energy, and that energy pushes outward, against the inward pull of gravity. Not violently, not explosively, just steadily. Constantly, a continuous outward pressure that matches almost perfectly the inward pull. This is the balance. This is what keeps a star from collapsing and keeps it from exploding. Gravity says, fall inward. Fusion says, push outward. And for billions of years they agree to meet in the middle. It's not a truce exactly, it's more like a stalemate. Neither side wins, neither side gives up. They just press against each other endlessly, holding the star in a state of suspension. And as long as that balance holds, the star continues. Think about it for a moment. Every star you've ever seen is being held together by gravity and torn apart by fusion at the same time. Constantly, without pause, the inward crush and the outward surge locked in this eternal quiet struggle. And somehow it's stable. Somehow. it works. That's what's so strange about it. You'd think something balanced on the edge like that would be fragile, unstable, ready to tip one way or the other at the slightest disturbance, but stars aren't fragile. They're remarkably stable, because the balance isn't delicate, it's self-correcting. If gravity starts to win, if the star begins to contract even slightly, the core gets hotter, denser, fusion speeds up, more energy is released, the outward pressure increases, and the star expands again. If fusion starts to win, if the star begins to expand too much, the core cools slightly. Fusion slows down, less energy is released. Gravity pulls harder and the star contracts again. Back and forth, adjusting, responding, never perfectly still, but never falling out of balance either. It's like a conversation that's been going on for billions of years, gravity and fusion speaking to each other in the language of pressure and heat, and the star itself is the product of that conversation, the shape it takes, the light it gives off, the time it lasts. We don't usually think of stars as being in a state of tension. We think of them as peaceful, eternal. But the peace comes from the tension. The stability comes from the opposing forces being perfectly matched. And that's why stars don't explode immediately. Not because they're holding back, not because they're being careful, but because the explosion and the collapse are happening at the same time, in equal measure, and cancelling each other out. As long as the fuel lasts, the balance holds. As long as the balance holds, the star shines. It's that simple, and that profound. When a star first forms, it's just a cloud, hydrogen mostly, scattered across space, thin enough that if you were floating in the middle of it, you might not even realize it was there. But gravity notices. Gravity always notices. And slowly, so slowly, it begins to pull. One atom drifts toward another, then another, and another. Over thousands of years, the cloud begins to gather, to shrink, to fall inward on itself. As it falls, it heats up. That's what happens when things compress. When you squeeze air into a smaller space, it warms. When you crush hydrogen under its own weight, it gets hot, very hot. And eventually, after millions of years of collapsing, the center of that cloud becomes so hot, so dense, that something changes. Fusion begins. Just a flicker at first. A few hydrogen atoms pressed close enough to merge. But that's all it takes, because once fusion starts, it doesn't stop. It releases energy, heat, pressure. And that pressure pushes outward against the collapse. For the first time, the cloud stops falling. It doesn't reverse. It doesn't explode outward. It just stops, suspended, held in place by the very thing that's happening at its core. And from that moment on, the star exists in this strange state, always on the verge of collapsing, but never actually collapsing. Because every time gravity pulls inward, fusion pushes back. This is what saves stars from their own weight. Without fusion, they'd collapse completely. They'd crush themselves down into something small and dense and dark. And we know this happens eventually. When the fuel runs out, when there's nothing left to fuse, gravity wins. The star collapses. It becomes a white dwarf or a neutron star or something even stranger. But while the fuel lasts, collapse is impossible. Because the energy from fusion isn't optional. It's not something the star can turn off. As long as hydrogen is fusing into helium, energy is being released. And as long as energy is being released, the star has to expand slightly to make room for it. Not enough to fly apart, just enough to resist falling inward. It's a kind of survival, not intentional, not planned. Just the natural consequence of what happens when you compress hydrogen till it starts to change. And here's the part that's easy to overlook. The collapse never really stops. Gravity never stops pulling. The star is always trying to fall inward, every second, every moment. But fusion keeps saying no, not loudly, not dramatically, just persistently, constantly. A steady stream of outward pressure that matches the inward pull exactly, and because that pressure comes from the core, from the very center of the star, it radiates outward in all directions. It pushes against every layer. It holds the entire structure up, the way a single pillar can hold up a roof if it's in the right place. So the star doesn't collapse, not because it's strong, but because it's active, because something is happening inside it, because the core is alive with fusion, and that aliveness prevents the fall. This is true for every star. The ones we see at night, the ones too far away to see, the sun that rises every morning, they're all holding themselves up the same way, all resisting their own gravity with the same quiet, continuous effort. And they'll keep doing it for as long as the hydrogen lasts, for as long as there's fuel to fuse, for billions of years in most cases, not because they're permanent, but because the balance between collapse and resistance is so perfectly matched that change happens slowly. So slowly that entire civilizations can rise and fall in the time it takes a star to burn through even a fraction of its fuel. The collapse is always there, waiting, patient, but for now, fusion is stronger and the star continues. Hydrogen is the simplest thing in the universe. One proton, one electron, nothing else. It's the first element, the most abundant, the building block of everything that came after, and it's everywhere, in stars, in planets, in the space between. If you gathered up all the atoms in the universe and sorted them, most of what you'd find is hydrogen. So when a star forms, it has plenty to work with. More hydrogen than it could ever use, it seems, enough to burn for a very long time. But here's what makes stars last. Hydrogen doesn't fuse easily. It's not reluctant exactly. It's just that the conditions have to be perfect, and even when they are, the process is slow. To fuse two hydrogen atoms together, you have to overcome something fundamental, something built into the nature of matter itself. Protons repel each other. They're both positively charged, and positive charges push away from each other. It's one of the basic rules, like charges repel, always. So if you want to fuse hydrogen, if you want to push two protons close enough that they stick together and become helium, you have to force them past that repulsion. You have to push them so close that a different force takes over. The strong nuclear force. The thing that holds atomic nuclei together once they're already touching. But getting them to that point requires enormous pressure, enormous heat, the kind of environment that only exists at the center of a star. And even then, even in the core of the sun where the temperature is 15 million degrees, fusion happens slowly. Not because the star is being careful, but because the odds of any two hydrogen atoms actually colliding with enough force to fuse are small. Most of the time, they just bounce off each other. They come close, they feel the repulsion, and they veer away. Nothing happens. It might take millions of collisions before a single successful fusion occurs, and in the meantime, all those other hydrogen atoms are just waiting, drifting, bouncing, waiting for their turn. This is the secret, really. This is why stars last billions of years instead of seconds. Because fusion isn't efficient. It's not fast. It's not even particularly good at converting hydrogen into helium. It's just persistent, slow, steady. At any given moment, only a tiny, tiny fraction of the hydrogen in the core is actually fusing. The rest is just there, waiting, held in place by gravity, heated by the pressure, but not yet participating. And that waiting, that long, patient queue of hydrogen atoms waiting their turn, is what gives stars their longevity. If all the hydrogen fused at once, the star would explode in an instant. A single brilliant flash, and then nothing. Just an expanding cloud of helium and energy. But it doesn't work that way. It can't. The physics won't allow it. Fusion is bottlenecked by the very forces that make it possible. The repulsion between protons, the need for extreme conditions, the randomness of collisions, so the star burns through its hydrogen one atom at a time, or rather, a few atoms at a time, slowly, gradually, over billions of years. It's not trying to be slow, it's not conserving anything. It's just that the process itself is inherently gradual, and because of that, because hydrogen takes so long to fuse, stars have time. Time to shine, time to hold their shape, time to exist in that delicate balance between collapse and explosion. The sun has been fusing hydrogen for 4.5 billion years, and it's only about halfway through. Halfway. After all this time, after all the light it's given off, after every sunrise and sunset humans have ever witnessed, it still has roughly as much hydrogen left as it's already used. That's how slow fusion is. That's how patient hydrogen can be. And that patience, that fundamental slowness built into the process, is what allows stars to exist at all. Without it, there would be no stars, no steady light, no billions of years of shining, just brief bright flashes in the dark, and then silence. 1 billion years is not a number we can hold in our minds. We can say it. We can write it down. We can use it in sentences, casually, as if we understand what it means, but we don't, not really. A human lifetime is, at most, 100 years, and even that feels long when we're living through it. Childhood feels like it lasts forever. A single year, when we're young, feels impossibly vast. But 100 years is nothing to a star. It's less than a blink, less than a heartbeat. It's a moment so brief the star wouldn't even register it if stars could register things. The sun has been shining for 4.5 billion years. Try to picture that. 4.5 billion years ago, there was no life on Earth, no oceans, no atmosphere as we know it. Just rock and heat and violence. The planet itself was still forming, still being bombarded by debris left over from the solar system's birth. And the sun was already there, already shining, already in the middle of its life. It watched the Earth cool, it watched the first oceans condense, it watched life begin, single cells in warm water, dividing slowly, changing even more slowly. It watched those cells become complex, become multicellular, become fish and plants and insects and dinosaurs. It watched the dinosaurs disappear. It watched mammals spread. It watched primates evolve. It watched us arrive, build cities, invent writing, look up at the sky and wonder what it was. And through all of that, every extinction, every ice age, every moment of every day for every living thing that has ever existed on this planet, the sun has been doing the same thing, fusing hydrogen, releasing energy, shining, steady, unchanged, patient beyond measure. And it's only halfway done. It will keep shining for another 4.5 billion years, long after we're gone, long after everything we've ever built has eroded away, long after the continents have drifted into new configurations and the oceans have risen and fallen and risen again, the sun will still be there, still fusing, still shining. That's the kind of time we're talking about when we talk about stars. And the sun isn't even particularly long-lived. It's average, ordinary. There are stars much smaller than the sun, red dwarfs, dim and cool, that will burn for 10 trillion years, maybe longer. 10 trillion years is longer than the current age of the universe. It's longer than anything else we know. longer than galaxies will stay together, longer than most structures in the cosmos will survive, and those small stars will just keep going, keep fusing, keep shining, outlasting nearly everything. We don't have words for that kind of duration. We don't have comparisons that make sense. It's so far beyond human experience that it stops feeling real, but it is real. Stars measure time in billions and trillions of years the way we measure it in days and months. And to them, if they could feel time at all, our entire existence would be too brief to notice. All of human history, everything we've done, everything we've built, every war and peace and discovery fits into a few thousand years. And a few thousand years to a star is nothing, less than nothing. It's a flicker, a fraction of a second in a life that spans eons. And yet somehow we're here, living in this brief moment, looking up at stars that were shining long before we arrived and will continue long after we're gone. There's something humbling about that. Something that puts everything into perspective. Not in a sad way, not in a way that makes us feel small and insignificant, but in a way that reminds us we're part of something much larger, much older, much more patient than we usually remember. The stars aren't in a hurry. They never have been. And maybe, just for tonight, we don't have to be either. Nothing lasts forever, not even stars. For billions of years the balance holds. Gravity pulls inward, fusion pushes outward, and the star stays suspended between the two, shining steadily, burning through its hydrogen one atom at a time. But eventually, always eventually, the hydrogen runs out. Not all of it, not everywhere, just in the core, the place where the pressure is highest. The only place fusion can happen. And when the core runs out of hydrogen, fusion stops. Not suddenly, not dramatically, but gradually. The rate slows, the energy output decreases, and without that outward pressure, without that constant push from the core, gravity starts to win. The core begins to contract. It doesn't collapse all at once, it just tightens, squeezes inward, gets smaller, denser, and as it does, it heats up. That's what compression does. It turns gravitational energy into heat. And something interesting happens. The shell of hydrogen around the core, the hydrogen that was never hot enough to fuse before, suddenly finds itself in the right conditions. Hot enough, dense enough, and it starts to fuse. So the star doesn't go dark. Not yet. Instead, it actually gets brighter. The fusion moves outward into a shell around the inert core, and the energy from that shell pushes the outer layers of the star outward. The star expands, swells, becomes larger than it ever was before. This is what we call a red giant. And it's not the death of the star. It's more like a transition, a shift from one phase to another. The balance hasn't disappeared. It's just changed. The core is no longer where the action is. The shell is, and the star adjusts to this new reality, finding a new equilibrium between forces. For a while it stays this way, large, bright, burning hydrogen in a shell around a dormant core. But that can't last either. The shell burns through its hydrogen too, and when it does, the cycle repeats. The core contracts again, heats up again, and if the star is massive enough, if the core gets hot enough, helium starts to fuse, helium into carbon, carbon into oxygen, and in the most massive stars even heavier elements. Each stage shorter than the last, each transition more dramatic. The star is running out of options, running out of fuel, running out of ways to push back against gravity, and eventually there's nothing left to fuse, nothing left that can release energy. The core becomes inert, dormant, just sitting there heavy and dense and cold, and without fusion, without that outward pressure, gravity finally wins. The star collapses. or explodes, or both, depending on how massive it is. But for most stars, for stars like the Sun, the end is quieter. The outer layers drift away, the core cools, and what's left is a white dwarf, a dense remnant, still hot from the compression but no longer shining, no longer fighting, just done. The balance, after billions of years, finally tips. There's a paradox at the heart of stars, and it's not immediately obvious. You'd think a larger star, one with more hydrogen, more fuel, would last longer than a smaller one, more material to burn through, more time before it runs out. But that's not how it works. The largest stars burn the fastest. They consume their fuel in just a few million years, sometimes less, a fraction of the time smaller stars take. Meanwhile, the smallest stars, red dwarfs barely massive enough to fuse hydrogen at all, can burn for trillions of years. More fuel, shorter life, less fuel, longer life. Seems backward, but it makes sense once you understand what's really happening. Because it's not about how much fuel you have, it's about how hard gravity is squeezing. A larger star has more mass, and more mass means stronger gravity. The core is under more pressure, more weight pressing down from above, more force trying to crush everything inward. And when the core is under more pressure, it gets hotter, much hotter. The temperature rises, the density increases, and fusion happens faster, not just a little faster, dramatically faster. The most massive stars fuse hydrogen so quickly that they burn through their entire supply in just a few million years. They shine brighter, hotter, more intensely. But they don't last. They're like fires fed too much oxygen. They burn brilliantly, but they consume themselves in the process. Smaller stars are the opposite. Their gravity is weaker. The pressure at the core is lower. The temperature doesn't rise as high, and fusion happens slowly, very slowly. So slowly that a red dwarf can stretch its hydrogen supply across trillions of years, longer than the current age of the universe, longer than most galaxies will remain intact. It's a strange kind of efficiency, not intentional, not designed, just the natural consequence of how gravity and fusion interact at different scales. The more mass you have, the harder gravity works, and the harder gravity works, the faster you burn. There is no way around it, no way to slow down. A massive star can't decide to take its time. The physics won't allow it. The pressure is too high, the temperature is too extreme. Fusion happens whether the star is ready or not. And because fusion happens so quickly, the star produces enormous amounts of energy. It shines thousands, even millions of times brighter than the sun. You can see massive stars from across the galaxy. They're the bright beacons, the landmarks in the night sky, but they're temporary, meteoric, here for a moment cosmically speaking and then gone. Smaller stars don't shine as brightly. You need a telescope to see most of them. Some are too dim to see even with the best instruments we have, but they're the survivors, the ones that will outlast everything else. It's almost like the universe is offering a choice. Shine bright and burn fast, or shine dim and last forever. Except it's not a choice. It's just physics, just the inevitable result of how much mass you start with. And there's something almost poetic about that. The biggest stars, the ones that seem most powerful, most dominant, are the most fragile, the first to go, the first to exhaust themselves. While the smallest stars, the ones we barely notice, are the ones that endure. Not because they're stronger, but because they're patient, because their gravity is gentle enough that fusion can happen slowly, sustainably. For timescales we can't begin to comprehend, the brightest stars burn out, the dimmest stars last. And in between, somewhere in the middle, is our sun. Not the largest, not the smallest, just steady. Burning at a pace that gives us time. Time for planets to form, time for life to begin, time for us to look up and wonder how long it will last. Long enough, as it turns out. For now, at least. The sun is unremarkable. There's nothing special about it, really. It's not the largest star, not the brightest, not the hottest or the oldest or the most unique in any particular way. It's just average, medium-sized, middle-aged, one star among hundreds of billions in the galaxy, doing what stars do. And maybe that's exactly why it matters, because average in this case means stable, reliable, steady enough that life could take hold on a planet nearby and survive for billions of years without being scorched or frozen or swept away by violent stellar outbursts. The sun has been burning steadily for 4.5 billion years. Every morning it rises, every evening it sets, the same light, the same warmth, generation after generation, species after species. It's never exploded, never dimmed unexpectedly, never varied in any way that threatened everything living beneath it. It just continues, day after day, year after year, millennium after millennium, and it will keep going for another 4.5 billion years, roughly, give or take a few 100 million. Long after we're gone, the sun will still be there. Still fusing hydrogen in its core, still holding the solar system together with its gravity, still shining on whatever remains. There's a comfort in that somehow, a kind of permanence that's rare in the universe. Not true permanence. The sun will end eventually. We know that. In 5 billion years or so, it will swell into a red giant. It will consume the inner planets, possibly including Earth. Its outer layers will drift away, and what remains will cool slowly into a white dwarf. But that's so far in the future it might as well be forever. For now, for the entire span of time that matters to us, the sun is constant. It was here before us, it will be here after us, and in between, it provides the light and warmth that makes everything possible. We don't usually think about it that way. The sun is just there, part of the background, part of the ordinary rhythm of days. But it's been shining since before the earth had oceans, since before life existed, since before anything we recognize as familiar took shape. And it will keep shining long after our moment has passed. That's what middle age looks like for a star. Not decay, not decline, just continuation. Steady, unremarkable, essential. The sun is halfway through its life and it's doing exactly what it's supposed to do, burning slowly, lasting long, giving us time. There are stars so small, so dim that we didn't even know they existed until recently. Red dwarfs, tiny compared to the sun, some barely 1/10 of its mass, glowing faintly in the darkness, putting out just a fraction of the light our sun does. You can't see them with the naked eye. Most of them anyway. They're too far away, too faint. Even with telescopes, they're easy to miss, easy to overlook, but they're everywhere. They make up roughly 3/4 of all the stars in the galaxy, the majority. The quiet background presence we never think about, and they will outlast everything. A red dwarf burns so slowly that it can stretch its hydrogen supply for 10 trillion years, maybe longer. We're not entirely sure because none of them have ever died. Not one. The universe isn't old enough yet. Every red dwarf that has ever formed is still burning, still shining, still in the early stages of its impossibly long life. 10 trillion years is difficult to grasp. The universe itself is only about 14 billion years old. That means a red dwarf could burn for 700 times longer than the universe has currently existed. By the time a red dwarf runs out of fuel, the universe will be unrecognizable. Galaxies will have drifted so far apart that most of the sky will be empty. Stars like the Sun will be long gone. Black holes will dominate what's left. And still, red dwarfs will be shining, quietly, steadily, outlasting nearly everything else. There's something almost comforting about that. The idea that long after everything we know has faded, these small dim stars will still be there. Still burning, still holding on. They don't shine brightly, they don't draw attention. They are not the stars we point to when we look up at night. But they endure. And endurance, it turns out, is its own kind of strength. Not the strength of burning hot and bright, not the strength of dominating the sky, but the strength of patience, of lasting, of continuing when everything else has stopped. Red dwarfs are survivors by design, not because they tried to be, but because their gravity is gentle. Their cores are cool enough that fusion happens at the slowest possible rate. They sip their hydrogen rather than gulping it down. And because of that, they have time, more time than anything else in the universe, more time than we can even imagine. The smallest stars will be the last stars, the final lights in a darkening cosmos, still burning, still patient, long after everything else has gone quiet. When we think about stars, we sometimes think about supernovas, those dramatic, violent explosions, stars tearing themselves apart in a final burst of light bright enough to outshine entire galaxies. They're spectacular, unforgettable, the kind of cosmic event that captures our imagination. But they're rare. Most stars never explode. They can't. They don't have enough mass. They're not built for that kind of ending. Stars like the Sun, and smaller, will swell and fade and drift away, but they won't explode. They'll just stop. Quietly. The outer layers will disperse into space, and the core will cool into a white dwarf. No violence, no drama, just a gentle end after billions of years of steady burning. Even among massive stars, the ones that do explode, most of their lives are spent in balance, instability. The explosion only comes at the very end when there's nothing left to fuse, when the core finally collapses under its own weight and rebounds in a shockwave that tears the star apart. But that's the last few seconds of a life that lasted millions of years. The explosion is the exception, the anomaly, the brief moment of chaos after an entire lifetime of order. Because the default state of stars, the thing they do most of the time, is shine steadily, exist in balance, hold themselves together through the slow, patient conversion of hydrogen into helium. The universe, it seems, is built for slowness, for gradual change, for processes that unfold across billions of years rather than seconds. Explosions make the news. They're what we remember. But they're not the norm. The norm is a star like the sun rising every morning, setting every evening, burning quietly in the balance between collapse and explosion, never tipping too far in either direction. And that's true for most stars, the vast majority. They're not on the verge of detonating, they're not unstable, they're not fragile. They're remarkably stable, actually, held in place by forces that balance each other almost perfectly. And they stay that way for timescales longer than we can comprehend. Gravity doesn't want explosions. Fusion doesn't want explosions. They just want equilibrium. And equilibrium is what most stars achieve. So when we ask why stars don't explode immediately, the answer is simple. Because explosion isn't the natural state. Balance is, steadiness is. And the universe, for all its vastness and strangeness, seems to prefer things that last, not things that burn bright and fast and disappear, but things that continue quietly, patiently, for as long as they possibly can. There's a lesson in all of this, though we don't have to call it that. Just an observation, really. Something worth sitting with. The things that last, the things that endure across unimaginable stretches of time, aren't the ones burning brightest or moving fastest. They're the ones that found balance, that settled into a rhythm they could sustain. Stars teach us this without meaning to. They don't last billions of years because they're invincible. They're not. They're constantly on the edge between collapse and explosion, always one shift away from tipping too far in either direction. But they hold that tension. They exist in it. And somehow that makes them still, not stable like a rock, not unchanging, but still like a conversation between opposing forces that's been going on so long, neither side remembers when it started. And that stability, that ability to hold two opposing pressures in balance, is what allows stars to shine. It's not dramatic. It's not exciting. There's no moment of triumph, no turning point where everything suddenly works. It's just continuation, day after day, billion after billion years, the same thing over and over. Gravity pulling inward, fusion pushing outward, neither winning, neither losing, just meeting in the middle endlessly. And maybe that's what stability actually is. Not the absence of tension, not the end of struggle, but the ability to hold opposing forces without breaking, without collapsing, without flying apart. Stars don't fight against the forces acting on them. They don't resist gravity or try to escape it. They just exist within it, held together by the very thing that wants to crush them, and that's enough. For billions of years it's enough. The brightest moments aren't always the longest. The loudest voices aren't always the ones that endure. Sometimes the things that last are simply the ones that found a way to stay balanced, quiet, steady, persistent, like stars. And so we come back to where we started. The stars above, still there, still shining, just as they were when we began, and just as they'll be long after this night ends. We've travelled through time tonight, billions of years, trillions even. We've watched stars form from clouds of hydrogen. We've seen them find their balance. We've understood, at least a little, why they don't simply burn out all at once. It's because of gravity and fusion, because of pressure and heat, because hydrogen fuses slowly, and balance takes time to break. But more than that, it's because the universe seems built for patience, for gradual change, for things that last not because they're dramatic, but because they're steady. The stars aren't in a hurry. They never have been. And maybe, just for tonight, we've learned to slow down with them, to sit with ideas that unfold gradually, to let understanding come at its own pace. You can stay here as long as you'd like. Let the words fade into the background. Let your thoughts drift. The stars will still be there when you wake. They always are. We've been here together, you and I, thinking about why stars shine for so long, why they don't collapse or explode, why balance, not drama, is what allows them to exist at all. And now you know, not because you memorized anything, but because you felt it. The slowness, the patience, the quiet endurance of things that burn steadily instead of brightly. If this felt right, if you'd like to return to this kind of quiet exploration, you're welcome back any time. We'll be here, taking our time, never rushing. Until then, the stars will keep shining, and so will we. Good night.